Okay, and back to recording again. So, starting off again, we're talking about things like the normal distribution, building the tools we need to do hypothesis testing. Now, we're going to need the simple things like the average of the data. We're going to need things like the variation in the data. And then from something like the variance, we can come up with the standard deviation, which here manifests itself in the normal distribution as these lines where we have cutoffs and say a certain proportion of the data falls into this range or this range or this range. And if I want to make a statement with a certain degree of confidence, I can say, I think the true number is this number. It could be as high as this and it could be as low as that. Depending on how confident I want to be, that range will be wider. So here I see for 95.44% confidence, I could give a point estimate plus or minus 2 standard errors and have a range like this. For exactly 95% confidence, we'll round that 2 down or unround that 2 down to 1.96, the magic number that we like to remember. Okay, so lots of that. But we'd like to get into looking at the relationships between variables so we can start talking about correlation and then build the slope of a regression line, which is maybe ultimately what we would like to be working with. So the next thing here, before we get into that, is tagging each observation with how far above or below the center of the distribution it is. Now, the idea we had in the previous video where we're talking about the difference between y bar for one group and y bar for another group was a very, very direct attack at that line of reasoning, testing the difference between two subsamples. But it may have been a little bit less obvious that that distance divided by the standard error was a measure of statistical distance between those two averages. The easiest introduction to statistical distance is a z-score, which is often called a standardized value. One of the things about data that is sometimes helpful and sometimes not helpful is the fact that everything is measured using units. And I would like it if the units I use don't impact the decisions that I make. So how would I arrive in a world where the units that I use don't impact the decisions that I make, and it doesn't matter whether I measure your height in inches or centimeters, and it doesn't matter whether I use Fahrenheit or Celsius? Well, statistical distance is going to be unitless, and it'll just tell me how far above or below average an observation is based on the standard deviation of the original data. Look at this. So I've got the number of standard deviations an observation is from the mean. The z-score is a measure of the relative location of the observation in a data set. Positive numbers are observations that are higher in the data set, and negative numbers are observations that are lower in the data set, specifically how many standard deviations above or below. All right, which is what it says here. A data value less than the mean will have a z-score less than 0. A data value greater than the mean will have a z-score greater than 0. And if an observation has a z-score of exactly 0, then it must be equal to the sample average, because the sample average is the only thing that would survive this formula here and turn into 0. Pay attention to the formula and what it's doing. I've got xi, which is an observation. So if I ask somebody how tall they are and they say, oh, I'm exactly 6 foot. I go, okay, you're 6 feet tall? All right. So convert that into inches. That's your observation, 72. Here I have x bar. Okay, x bar is the average of the sample. So whatever the original observation was, subtract the average, and it just tells me how far you are above or below average in the original units. But if I don't want the original units, and I want a measure of statistical distance, I'll divide that by the standard deviation. And you'll notice here, I've got lowercase s, which is the sample standard deviation. If I knew the true population standard deviation, of course, I could use the Greek letter sigma, and sometimes you'll see that in the notation where people imagine that we already know the true population standard deviation or something about the average, in which case I might replace x bar with mu. But this x bar is just the regular add up the data and divide by how many there were. So what happens? If somebody is 3 inches taller than average, and I divide by the standard deviation, which was 3 inches, then I say this person is exactly 1 standard deviation taller than average. Go back to the picture. And I can find exactly where that person lives on this graph. Now, this graph could be the histogram of the original data, and all I have to do is change the units on the horizontal axis. If the original average was here, instead of mu, I'd see a number, and instead of mu plus 1 standard deviation, I'd see that number plus 3 inches, which was the 72 we just had, and I'd say this person is in fact 1 standard deviation above average. There's going to be somebody else out there in the universe who's 1 standard deviation below average, and so on and so forth. That's what we're doing here. Just converting x's into z's. All right. Example. The standardized values for apartment rents. You'll remember this set of apartment rents that we had in another video a couple of days ago. So if I take the smallest number that was in that set, which happened to be 525, and I subtract the average from that set, which happened to be 590.8, and I divide by 54.74, which was the standard deviation in that set, my 525 gets remapped to a new set of units, which are no units except statistical distance. It becomes negative 1.2. And it says this apartment is actually 1.2 standard deviations below average in terms of its rent. That means it's cheap. And then I see that there are many apartments that are below average in terms of their rent. You would notice that I'm seeing negative numbers all the way down into the 5th row here. So in fact, most of these apartments are below average in terms of their rent. This distribution is a little bit skew. The mean and the median are not quite the same number here. So that's why that's happening. Most of them are negative, but most of them are also very small. These very small numbers like 0.38, 0.34, negative 0.01 are close to 0 because these apartment rents are close to the average apartment rent. And it doesn't get any larger than, you can't see it because I'm covering up the, here, I can fix that. It doesn't get any larger than 2.27 over here on the right. So these apartments are more than 2 standard deviations above average in terms of their price, but that's all that a z-score is. You'll notice that there's 1 z-score for every observation in the original data. It preserves the shape of the distribution. It just turns everything into how far you are above or below average. Now, remember, we said previously, in something like a normal distribution, 95% of the data would be within 1.96 standard deviations of the mean, which means only 1 out of every 20 observations could be beyond that cutoff, 2 standard deviations. Here, I see them. I see the 2 observations that are more than, well, actually, look, it matters whether I use that cutoff at 2 standard deviations or whether I use 1.96. So 95.44% of the data is going to be within 2 standard deviations, and only something like 4.5% can be above 2 standard deviations away from the mean. There's nothing in the left tail that far away from the mean, but here there are 2 observations in the right tail that are above average beyond that point, more than 2 standard deviations above average. If I use that 1.96 cutoff, where only 1 out of 20 observations can be above that, I see 1, 2, 3, 4, 5, 6 observations above that. And you may look at that and say, well, okay, there were not that many observations here to begin with. I wonder about these proportions, and I wonder about that normal distribution, and I wonder if using the normal distribution is the best idea in every case. I do know that this is a skew distribution. I've got a lot of observations that are negative, but none of them are very large, and I have fairly large observations here on the right. The good news is we do have some generalized theory as far as what the distribution could look like. One of the big topics in applied statistics is whether we can use the normal distribution or whether we should stay away from that shape because it seems so very artificial. And of course, if you see the formula for this thing, you'd wonder how on earth anything in nature can abide by this rule, but as it turns out, there are things in nature that abide by that rule. And I'm not saying that because I'm dogmatic, I'm saying that because the central limit theorem tells us that the sample average will abide by this nice ideal shape in a large sample, and it's a theorem. So we're going to rely on that and use the normal distribution quite a lot. There is a generalized theory that tells us, in fact, even when the normal distribution isn't correct, there are still some hard bounds for how much data can be a certain distance from the mean in terms of statistical distance. Chebyshev's theorem says at least 1 minus 1 over z squared of the data values must be within z, standard deviations from the mean, where z is any value greater than 1. So for instance, if I plug in z is equal to 2, this works for any number, by the way, any number greater than 1. Plug in 2, and then come back to here and say, okay, 1 minus 1 over 2 squared, that would be 1 minus 1 over 4. So 1 minus 1/4 is 3/4. At least 3/4 of the data must be within 2 standard deviations of the mean. Well, sure enough, I've got way more than 3/4 of the data here within 2 standard deviations of the mean, just relying on these z-scores to tell me that. And then turn it up a notch. At least 89% of the data must be within 3 standard deviations of the mean, and at least 94% of the data must be within 4 standard deviations of the mean. So even though this shape is likely to be wrong, in fact, it's almost guaranteed to be wrong for your sample. When we talk about the distribution of the average, it's almost guaranteed to be right. But for your sample, I don't expect your sample to look like this. But there's a theorem that tells me exactly how far off that could be, and that's a little bit comforting in some way. So in the case of the apartment rents, you just pick any z you like. You could choose 1.5. X bar is 590, and the standard deviation was 54.74. Well, okay, plug it into Chebyshev, and you'd say, 1 minus, this comes out to 0.44. 56% of the data should be within that distance from the true average. And okay, x minus z, 1.5 times this, 509, 673. Okay, so I have a lower bound, 509, and I have an upper bound, 673. Look, I'm using the formula for a confidence interval that we just covered in the previous video. Take my average, add 1.5 standard deviations, and 509 to 673 is a range that should cover, according to Chebyshev's theorem, 56% of the data. And that is the worst possible case. In this case, it's 86%, which is really quite a lot better. So all of these confidence intervals tell you something about the probability that you're wrong. That probability might be overly conservative in many cases. So if I say I think there's a 56% chance that your apartment is between these numbers, which is a bit silly because these are numbers from another place and old numbers as well. But in whatever place these numbers came from, if there's a 56% chance your apartment is in that range, I'm going to be right way more often than I think I would have been. So being right too often is not a bad problem to have. That's the point. If you do believe that the data look approximately like a bell shape, whether you believe that it's truly this bell shape or just something pretty close, right? It's not that bad of a problem to rely on this empirical rule and say 95% of the data should be within about 2 standard deviations, and 99.7% of the data should be within about 3 standard deviations away from the mean. And the 68, 95 numbers are numbers that people tend to hang on to in their memory. So, not bad. Next, we should talk about detecting outliers. Now, there is a data set on our website that has to do with transformers, and it shows up on the first homework, and I hope everybody has a laugh when you see it. You'll notice that it is a data set talking about the height of individuals, and there are just a couple of people in there, and it says how tall they are. One of those people is named Optimus Prime, And if you know anything about transformers, you'll know that Optimus Prime is a giant robot from space. So when you see Optimus Prime in that data set, you might immediately start to question whether he belongs in there with everybody else. If I want to know how tall the average American is, do I consider Optimus Prime? Suppose I go out and I'm giving surveys to everybody, and I'm hiring other people to help me, and they're giving surveys to everybody because I'm trying to conduct a large-scale sample. One of these observations was from Optimus Prime. Well, outliers are observations that are different from the rest of the data, and there is no perfect way to identify them. I can recognize Optimus Prime as a giant robot from space, but in order to look at the data and choose which of the observations in a given data set are outliers, I have to come up with some sort of a rule, some sort of a preference-driven way of tagging who I think is or isn't an outlier. And this classical rule is one of those, but it's imperfect. It doesn't work all the time in identifying observations that came from a different distribution. Okay, I'm just saying this is a rule. Maybe not one size fits all. But perhaps the most common rule for tagging outliers is a data value with a z-score less than -3 or greater than +3. The idea here is if the data came from a normal distribution, these observations more than 3 standard deviations below average and these observations more than 3 standard deviations above average are exceptionally rare. So if I see something like that, I start to wonder if it really came from a normal distribution. And if most of my observations came from a shape like this, and then there's a cluster of observations that are, say, 5 standard deviations above average, I start to wonder if those observations are from the same family as everybody else, or if something weird happened. Now, this is a good idea if you're thinking that your data might have been typed in with error. If you're working with data that was manually entered by someone who works for you, or perhaps someone who works for you who doesn't care that much about the details, well, you might have a typo from time to time. And if the typo is an extra 0 at the end of a number, it's going to make that number very easy to identify relative to the other numbers, especially if there's not that much variation in the other numbers, which means that those have a small standard deviation. So sometimes this is a very helpful thing to do. Also, if you see negative numbers in data that shouldn't have negative numbers, you may start to think those are outliers, or that they are tagged in some other way. Incorrectly recorded data, data that was incorrectly included in the data set when it belonged in a different data set, or sometimes outliers are correctly recorded data that do belong there, and there's a risk associated with throwing them out because they might be very informative. There's a big debate in statistics. Robust statistics is a field of statistics that's all about basically dealing with outliers and dealing with the influence that outliers can have on the ultimate decisions that you make in a context like hypothesis testing. And in robust statistics, we frequently think about putting less weight or throwing out outliers and say, ignore that data. It looks erroneous in some way. But the price you pay there is those strange observations may have been the most interesting observations in the data set. So if you have somebody who gets an MBA and goes on to make $20 million, should I consider that person as one of my students who I should not study, or should I consider that person as one of my students who I should study more than anyone else? It might be the latter. Okay. Now, next step, putting two variables together. And we can stick with the z-scores and talk about the relationship between this formula and the counterpart of this formula that uses z-scores. Spoiler alert, it's called correlation, and you may have seen it before, where all the numbers get small. No, it's actually, yeah, we'll develop that relationship later. But the covariance between two variables is a special form of the variance that we saw earlier. So covariance, you might infer from the word that it has to do with how things vary together, how they co-vary, and watch what's happening. I'm going to take the average of something special now, x minus its own average times z minus its own average. When x is above average, I get a positive number here in that first bracket. When z is above average, I get a positive number here in this second set. If x and z tend to be above average at the same time and below average at the same time, notice what will happen. I get a positive number here and a positive number there when they're positive, or I'll get a negative number here and a negative number there when they're negative, but two negatives multiplied by each other becomes positive. Covariance will capture, in fact, the same information as correlation, which is derived from this, but it captures how much x is above average when z is above average. If there's no relationship between them, the covariance will be 0 because x isn't above average most of the time and z isn't above average most of the time, and this part by itself is 0 on average. That part by itself is 0 on average. But if they happen to move together, I get a positive number. And if they happen to move in opposite directions, so that x is above average and z is below average, and vice versa, then I always get negative numbers. Okay, great. It's a measure of the linear association between x and z. Its units are units of x times units of z. I was very excited for a moment until I realized that the units of x multiplied by the units of z may again be something. It seems like an anomaly, especially if x is measured in miles and z is measured in kilometers, and then I wind up with miles times kilometers or some ridiculous units that don't make any sense. So the size of a number for covariance is frequently something that's difficult to interpret. Covariance is usually looked at as either being positive or negative. We check the sign. And depending on the original units that you used, it could be very large or very small. You'll notice that we haven't thought about statistical distance here like we had with z-scores, where units don't matter. So this is it. This is all we infer. Positive covariance means a positive relationship between x and z. If they're independent, then there's no covariance. There are special cases where they have, say, nonlinear relationships, and I could still cook up 0 covariance with dependence. Okay, and there's the special trivia where covariance of x with x is going to look like this: x minus mu of x and x minus mu of x. Oh, that would simplify to x minus its own mean squared, which you recognize as the variance of x, which would just have units of x squared. So looking at this, I presume, based on what I now know about correlation, that there's a downward association between the student-teacher ratio in these classes in California and the test scores in these school districts in California. So the covariance is going to be negative. Correlation is going to take the same idea, and because the units have become the thorn in my side, we're going to get rid of those and use something unitless like the z-scores, which will still be negative. Okay. One quick aside here: the covariance for samples and populations exhibit the exact same phenomenon as the variance that we talked about a minute ago. So there is a formula for a population that divides by n, and there is a formula for a sample that divides by n minus 1. And if you do this in Excel and see two different versions of a formula for covariance in any sample, you're going to want to stick with this one. And if you see the Greek letter sigma, xy, that refers to a population covariance, which I'm almost never going to have. And if you see the lowercase s, Latin s, xy, that's referring to a sample covariance, which is in fact the average of xi minus its own mean and yi minus its own mean. So you see the formula here. How much is x above average when y is above average? Add those up, divide by n minus 1 in this case, and that's the average of this phenomenon, like we saw. Okay, same idea. Very good. So that's the formula. Correlation will take the covariance, which has units of x multiplied by units of y. That sounds terrible. What can I do with it? Well, take that covariance and divide by the standard deviation of x, which has not only the scale of x, but the units of x attached to it. That will take your covariance and annihilate the scale of x and the units of x. Then divide by the standard deviation of y. That will take the remaining scale of y in the covariance and units of y in covariance and wipe them out. You probably already know that correlation is always between -1 and 1. So correlation is the famous thing that we like to use instead of covariance because it has no units and it's easy to interpret. Values near -1 indicate a strong negative linear relationship. Not only that the relationship is downward sloping, but it has a lot of explanatory power. And values near +1 indicate a strong positive linear relationship. Not only that the variation is upward sloping, but it has a high amount of explanatory power. So I'd go out on a limb and look at this and say, the correlation is going to be negative because I see lower test scores over here for the high student-teacher ratios and higher test scores over here for the low student-teacher ratios. I see a downward slope. But I think it's going to be negative, not that close to -1, because there's a lot of variation here. It doesn't look like a line. It doesn't look like just knowing student-teacher ratio is going to allow me to predict the test scores. I think there are many things happening and a small correlation relative to the other variation that's happening in the data. So I'd guess maybe -0.2, something in that neighborhood, perhaps -0.3. Okay, the closer the correlation is to 0, noting that the numerator in this formula is covariance, hey, if covariance is 0, then there's no correlation between two variables, and if correlation is 0, then there's no covariance between two variables, meaning that there's no linear association. And if I tried to fit a line to this data, it would be perfectly flat. Fair enough. An example. Okay, so a golfer is interested in investigating the relationship, if any, between driving distance and the 18-hole score. We actually did an example like this in my DA291 class last semester. I had a couple of students from the UNA golf team. One of them happens to hit some very, very long drives, like way longer than this. And we looked at their average, and we looked at their average scores for the courses that they had been playing, and the standard deviation. And I tried to get them to test the null hypothesis that their population average, their long run scores that they would be getting for a round of golf were higher or lower. And I said, hey, you're not, you shouldn't be hitting this. You should be hitting that. And you couldn't reject the hypothesis. So it was kind of fun. So, okay, it was exactly this. It was driving distance and 18-hole score. What could I do with this? Well, I could come up with the average of all of these. I could come up with the average of all of those. I could come up with the standard deviation of all of these and the standard deviation of all of those. And I could think about looking at correlation between them. You might think that the UNA golf players who hit longer drives are getting lower scores for a round of golf, or for 18 holes. So here we go. Suppose that the average for all of these x's comes out to 267. The average for all of the y's comes out to 70. What do? I take x minus x bar. I take y minus y bar. Ignore the rounding here. But say that this difference, 277.65 minus the 267.0 comes out to 10.65. Okay? yi minus y bar, well, yi was 69 and y bar was 70, so y minus y bar comes out to -1. Does the sign matter? Yes, it does. Okay. xi minus x bar times yi minus y bar comes out to -10.65 in this case, and then I say I have a -7.45 in the next case, and so on. Add them up, 35.4, and divide by however many there were. You will come up with the variance. The square root of that will give you the standard deviation. Okay. Sorry, I just said variance and standard deviation. Covariance And if you divide that by the standard deviations of each, you will get correlation. So easy peasy formula to go through, nothing too serious. These tools that were on the slides a couple of lectures ago, correlation and OLS regression, are built on the same foundation. So when we get to fitting a line to some data here, y is equal to beta 0 plus beta 1x, the formula for the slope of a line, look at the pieces that went into it. The sum of all the xi minus x bar times yi minus y bar is exactly the covariance multiplied by the n minus 1. And look at the denominator here. The sum of all the xi minus x bar squared is exactly the variance of x multiplied by the n minus 1. So I have here a ratio of the covariance of x with y divided by the variance of x. Contrast that with the other one. Correlation was the covariance of x with y divided by the standard deviation of x and the standard deviation of y. Well, if I had divided it by the standard deviation of x twice, the standard deviation of x times the standard deviation of x would be the variance of x. So the only difference here is whether I divide by the standard deviation of x or whether I divide by the standard deviation of y. And that cute little fork in the road will give me one of two options. I told you that correlation was unitless, which is pretty cool. It's always between -1 and +1. Covariance. The OLS regression slope, the slope of the line, is rise over run. Rise is measured in units of y, and run is measured in units of x. So when I say one more unit of x correlates to this more units of y, I would like to know what that looks like with the units preserved, and specifically units of y divided by units of x. So start with the covariance, which has units of y multiplied by units of x. Divide by the standard deviation of x, as we did here, and the units of x are gone. If you then divide by the units of y, the units of y will also be gone. But if you divide by the units of x, the units of y are preserved, and you wind up with units of x in the denominator. All right. In fact, correlation and the slope of the OLS regression line are both based on the covariance. And all three of these, covariance, correlation, and OLS regression slope, are the same information repackaged with different units. We're going to use that to a fair degree to wrap these up in the same ideas, but they're all capturing this linear association between two variables. Okay, great. We'll test in any of these cases whether that linear association between variables is large or small or perhaps different from 0. I could propose the hypothesis that the correlation between x and y is 0, or that the relationship between student-teacher ratios and standardized test scores is no relationship. There's no correlation there. And I could test whether the slope of a regression line is different from 0. These are all the same ideas. In each of these cases, all I would need to know is how much higher or lower than average that estimate should be in a typical sample, something like the standard error. And then if I see that I've come up with something which is really far above 0 or really far below 0, I might ultimately reject the null hypothesis that there was no relationship between these two variables. Hence, Module 2 coming up very soon. So back to our most important tools, hypothesis testing. Compare the sample to a hypothetical state of the universe. If your sample gives you an estimate and a confidence interval that say there's a 95% chance this hypothesis is false, then you can reject that hypothesis with 95% confidence, essentially making a probabilistic decision. Notice that the decisions that we're making in this context are not always right or always wrong. Because we're using statistics and making probabilistic statements, I can reject a null hypothesis with 95% confidence, meaning there should be no more than a 5% chance that I'm wrong. But if I need to be 99% confident, I can ask for a higher threshold, and so that I will only reject and be wrong 1% of the time. Each of these hypotheses can be couched in any of those frameworks with any amount of confidence that you want, and depending on how much data you have, you may be able to reject or you may fail to reject at a given level of confidence. So we'll try all of these things. And then a p-value is ultimately going to tell us exactly how likely it is that we would see the data we have if that null hypothesis was true. So after we build all of these pieces, we'll eventually get to the p-value and say, you know, that whole logical process will boil down to one number, which might do a lot of the work for you. So that's something to look forward to. Okay, that's the end of the Module 1 slides. So look for a video about Excel, simple statistics, and then a video about deriving and using the OLS estimators, which is going to be a lot of whiteboard action. Those will be available soon.